Good morning, chemists. Good morning. Happy Friday. How are you? Everyone doing well? Okay, then let's start. If everyone's doing well and everyone's excited to learn about organic chemistry, then say no more. I'll teach you about organic chemistry. So we're in the beginning of 12-10 now. So we are going to learn about peroxycarboxylic acids. So a few of you have asked me questions about this from the homework, and I said we haven't gotten to it yet. Here we are. So what is a peroxycarboxylic acid? Well, remember what a carboxylic acid is. We have this carbon with a double bond to oxygen, and then we have an OH, just one oxygen with a hydrogen on it. But here for a peroxycarboxylic acid, we have oxygen, oxygen, hydrogen. So it's a peroxy group, like peroxide. Remember peroxide? H-O-O-H, peroxide. So this is a peroxycarboxylic acid, where now, again, we are polarizing this bond. Just like we were polarizing, remember the bromine-bromine bond, and we could polarize it, giving one of those a partial positive and one a partial negative? Well, we can do the same thing here with the oxygen-oxygen bond. We are polarizing that bond, moving electrons toward the green oxygen away from the blue one, giving the blue oxygen a partial positive charge and making it electrophilic. So we can react an alkene with, you're fine. We are going to react an alkene with a peroxycarboxylic acid, and then we're going to make an oxycyclopropane, along with just a regular carboxylic acid. So what are our peroxycarboxylic acid reagents? Well, one of them is this peracetic acid. So it's like acetic acid, but it has the oxygen-oxygen, or peroxyethanoic. So this is the common name here. And then here's our IUPAC. But we have this CH3, and then we have that peroxycarboxylic acid group. We have that same peroxycarboxylic acid group here, but then we have a benzene ring. This is called metachloroperoxycarboxylic acid. This is another common name. We'll learn about this in chapter 15. We'll learn about the naming of these benzene-containing compounds. But just for now, just know this as MCPBA. So if you see MCPBA over the arrow, know that you're going to be making an oxycyclopropane from the alkene. Now, the old name for oxycyclopropanes was epoxides. We used to call them epoxides. So this is called an epoxidation, but really we call them oxycyclopropanes now instead of epoxides. So when we are doing this reaction is a syn addition. Syn addition meaning that the two bonds to oxygen are added on the same face. The two bonds to oxygen are added to the same face of the alkene. Not one above and one below, but the two bonds to oxygen are added on the same face. So if they're added on the same face, then the stereochemistry of the starting material, this being a transalkene, needs to be maintained. And so again, these two these two methyls are trans to one another. One's in the back and one's in the front. So what do we have here? We have MCPBA, and then we have the solvent with MCPBA. Remember, dichloromethane, DCM, or CH2Cl2. So in this reaction, I want you to see that if this is how you'll really see the trans double bond drawn, right? We'll see it here without showing the hydrogens and the CH3s. And so over the arrow, we would have MCPBA and CH2Cl2. Something that I see students doing often is this. They'll draw this oxycyclopropane, and then they'll say, oh, okay, this bond is up, so I'll draw it up, and this bond is down, so I'll draw it down. This is not correct. This is not how you show stereochemistry. This is not how it's depicted here. We need to show stereochemistry in this way. So we still have our oxycyclopropane, and we have one of the methyls we can pick. It can be on a dash or it can be on a wedge, but then the other has to be the opposite because this is trans for the alkene. Both of them are pointed down, and we have here one as a wedge and one as a dash. So both of these groups are pointed down, and then one is a wedge and one is a dash. Or you could do this. This is fine. This is the same thing, but now both would be pointed up. And one is a wedge, one is a dash. Either of these are fine. This, no, not how this is depicted. Also, not this. Don't try to do this. This is going to mess you up when you think about stereochemistry for future reactions. So don't do either of these here. Not how this is depicted here, but these two are totally acceptable over here to the right. Questions on that? All right, so the mechanism for this reaction is something that we actually saw. If you were in my class, we actually saw this last semester. When did we see this? During the mechanism lecture in lab. Remember the mechanism lecture we did in lab? I think when we were doing IR. So we looked at this mechanism, and now we're going to look at it in more detail. So this would be, for example, MCPBA. Here, where this would be that benzene ring. The R would be the benzene ring, but it could be that peroxyacetic acid also, where R is just a CH3 group. But either way, we have here our alkene and our MCPBA. What is the mechanism for this reaction? Well, the first thing that happens is this arrow. This is arrow number 1. Why is that arrow number 1? Well, remember, we said that this oxygen that's furthest away from the carbonyl, that has a partial positive, and this one has a partial negative. So this is electrophilic with that partial positive, and so we use the electrons in our double bond to attack that carbon, giving us the oxygen-carbon bond. So we make this bond with arrow number 1. We've made that oxygen-carbon bond. Now, if we make that bond to oxygen, oxygen has a full octet here, so something has to give. We have to do this arrow here. This is our arrow number 2. Now, with this, we're moving electrons. Remember, the other oxygen has a partial negative, so electrons are being pulled toward it, but it can just pull it toward it, and we can get an oxygen with a negative charge, or it can say, oh, I'll just pivot them. So from the middle of the bond to the middle of the bond, from the middle of the oxygen-oxygen bond to the middle of the oxygen-carbon bond, this gives us the double bond we see here in the product. But now looking at this carbon had a full octet, so it can't have a double bond and another double bond, so something has to give. Some electrons have to go away, so we can do this third arrow. And so with this third arrow, the oxygen, remember this has a partial negative, this oxygen, because the carbon has a partial positive, so electrons are being pulled toward the oxygen there. And so the oxygen could just keep the electrons, but it says, oh, I see something close by. There's something nearby that instead of having an oxygen with a negative charge, it can be protonated. And so here we have this hydrogen that is vaguely acidic because this is a carboxylic acid, right? It's a peroxycarboxylic acid. So we draw that third arrow from the middle of the carbon-carbon double bond to this hydrogen. And so we are making this bond here. We're breaking the carbon-oxygen double bond, but we're making an oxygen-hydrogen single bond. We've pivoted those electrons. Oxygen was sharing electrons with carbon. Now oxygen is going to share 2 of its electrons with hydrogen instead. So now something has to happen to the electrons in this oxygen-hydrogen bond. We have an oxygen-hydrogen bond, the original electrophilic oxygen, and the hydrogen that it was bonded to. If we're taking that proton, something has to happen to those electrons. And also, remember, with the arrows that we've shown, all we've made is this bond. All we've made is this carbon-oxygen bond here, where now one of the carbons, this one here, would have a positive charge. So instead of leaving that as a carbocation, we can bring in more electrons. So we bring in this arrow number 4, where now oxygen says, oh, I have more electrons that I can share with you now. Because I lost that hydrogen that I was sharing electrons with, now I can share them with you, carbon that had a positive charge. And so in this, we draw these 4 arrows. They have to start at the correct place. They have to end at the correct place. But with these 4 arrows, this is a concerted reaction, right? Everything is happening all in one step. It's not a stepwise mechanism. Everything's happening all in one step. And in the end, we get our oxycyclopropane and we get a carboxylic acid. Carboxylic acid is now the leaving group, basically. Questions on that? All right, so for this reaction, what if we have 2 alkenes in the same molecule, but we're only using 1 equivalent? If we're only using 1 equivalent, but we have 2 alkenes, only one of those will turn into an oxycyclopropane. Only one of them will, because we only have 1 equivalent. If we had an excess, then both would react. But here, because we only have 1 equivalent of our peroxyacetic acid, that we're only going to be able to put the oxygen on one of these double bonds. So we have a disubstituted and we have a monosubstituted. It turns out that the greater the alkyl substitution, the more reactive that alkene will be. So we have more electron density being pushed into the alkene, and so our disubstituted alkene, that's the one that becomes the oxycyclopropane, whereas nothing happens to our other alkene. So let me draw this to show you something else here. And I'm going to give this some stereochemistry. So we have our double bond, and I'm going to give this some stereochemistry because it is the chiral carbon. So if we do this reaction, so same conditions that we see here, same conditions, but if we do this reaction, we're going to get some products here where we need to show stereochemistry. So remember I said, everything that we're doing in here, stereochemistry matters. So one of our products will be this. So nothing happens here. Double bond there. One of our products will be this. Oxygen is added between those 2 carbons that were the double bond. Now we're going to put, because it's a Syn addition, we're going to add stereochemistry there to that oxycyclopropane ring. But then we're going to get the other product there. Where again, the stereochemistry won't change here. But now we're going to get the opposite stereochemistry for the oxycyclopropane because that's where the reaction is happening. Remember, the starting material, trigonal planar. And so if it's trigonal planar, the reaction can happen above or below the plane. But both of the oxygen bonds get added either both below or both above the plane. And so we end up with these 2 products that are distereomers of one another. So they're formed in unequal amounts. So it's probably going to be that this one is major because we're adding the oxygen to the opposite face of this large ethynyl group. The other thing I want to point out here is notice how I'm drawing the stereochemistry here versus how I told you to draw the stereochemistry if we had this MCPBA reaction. Right? When we did this MCPBA reaction, we're showing the stereochemistry here with the bond to the methyls. But if we have an alkene in a ring, we show the stereochemistry with the bonds to the oxygen. So if your alkene is a part of a ring, then you either draw the oxygen bonds, those carbon-oxygen bonds above the plane or below the plane. But if you have just like these alkyl chains, so up here we have alkyl, alkyl. If you have these alkyl chains and it is an acyclic starting material, then you show the stereochemistry with the alkyl groups. All right, so this is acyclic alkene. Show the stereochemistry with the alkyl groups. So wedge dash for the methyls. if it is cyclic, so here we have a cyclic alkene. With the cyclic alkene, you're going to show the stereochemistry with these bonds, the carbon-oxygen bonds. So if we had, instead of having one equivalent, so I'm starting off with that same starting material. If we had two equivalents of our peroxycarboxylic acid, so two equivalents of it up here, then we'd end up with this mixture of diastereomers, where we could do the epoxide here, and we could do the epoxide here. We'd get both of these epoxides being on wedges, both of them being dashes. We get all this big mixture of products. But again, we would show our stereochemistry in this way. So here's one example of the products. We're showing our stereochemistry here in this bond to the ring versus us showing the stereochemistry in those two bonds of the oxycyclopropane because that is on the ring. Questions there?
Yeah, Professor, I got a quick question on this. So on the top, you kind of showed that so the oxycyclopropane formed in two sides. So is that because we used MCPBA?
No, it's the same reagent. MCPBA and this are the exact same type of reagent. What were you saying? I showed that the methyls on the front and the back. Is that what you're saying?
No, the two equiv thing that reacts.
Oh.
Yeah, why does it have the oxycyclopropane on the tail?
This would react also. Here we only had one equivalent. If we only have one equivalent, the whole point of this slide is the greater the substitution, that's going to be the one that reacts. The other one won't react. The other alkene won't react. But if we have two equivalents of whatever the peroxycarboxylic acid is, then both of our alkenes will end up reacting. Or if we have an excess.
So many rules.
I mean, it's molar equivalence. Like, it's just, this is, if you only have one, then that one equivalent will react with the only thing it can react with, the most reactive alkene. But if you added more, now you can have everything react. So, right, when we did the hydrogenation, if I only gave you one equivalent of hydrogen, then yeah, only one of your alkenes would react. But if you have an excess, then you can have all these alkenes that can react with that excess.
So like for these, the mechanism is not important, right?
No, this has the same exact mechanism as this. Same mechanism.
Okay, gotcha. Thank you.
Other questions?
Yeah, in that case, would it be racemic or still?
In this top case?
Yeah.
You would get some things that are racemic, and some other things that are racemic, and you get things that are diastereomers of each other.
Okay, cool. Thanks.
So I just drew one of the possibilities, one of the stereochemical outcomes, but you know that you could change it and have two bonds as wedges and this one as a dash, and two bonds as wedges and this one as a wedge. You can have all these different stereochemical outcomes. All right, so, go ahead.
Quick question. So, why did you say that the one on the wedge was major?
Down here. This is major because here, what's happening, remember on this carbon, we also have something else there. We're just not showing it, but we know there's a hydrogen there. So what's better? For this large, remember how big this is? This is large reagent. This large reagent, is it better for that large reagent to come in on the same side as the hydrogen, or here on the same side as this ethynyl group? It's better for it to come in on the same side as the hydrogen, adding these oxygens, because it's large. It's better for it to come in on the same side as a small group, all hydrogens on the top.
Okay, thank you.
All right, so with those oxycyclopropanes, we can ring open them. So we had one step where we have basically our MCPBA or any kind of peroxycarboxylic acid, and then a good solvent for that. And then we have a second step that is basically our aqueous workup step, but it's not the same kind of aqueous workup step as we've done before. This one is actually going to ring open the oxycyclopropane, giving us a vicinal dihydroxy group. So we get this vicinal dialcohol here, two alcohols in the vicinity of one another formed after this MCPBA reaction. It has to be two separate steps. You can't just throw everything in at one time. It has to be two steps. So what we have here is MCPBA adding one of the oxygens. And then the other oxygen, they've color-coded it, comes from the water. One oxygen comes from MCPBA, the blue one, and the other oxygen comes from water, the pink one. This hydrogen, though, would come from the acid. So we can add any kind of a nucleophile in here to bring open an oxycyclopropane. You've seen that before. You know that. Before we've used an oxycyclopropane being ring opened by a Grignard. Oxycyclopropane being ring opened by a Grignard. You've seen that, Grignard as the nucleophile. But we could use water as the nucleophile. So here, water is the nucleophile. We could use a strong base like hydroxide as the nucleophile also. But here we are going to be doing this where it opens on the opposite face to where the first oxygen was. So we get an anti-product. One oxygen at the top, one oxygen at the bottom. So this first reaction is a Syn addition. When we add the two bonds to oxygen for the MCPBA reaction, that is a Syn addition. But after the second step, it's it's an anti-addition. It's an anti-addition overall. We get an overall anti-addition. Syn addition the first step, but second step it's anti overall. So let's look at this. Stereochemistry of the starting material is maintained in the course of the reaction, but it is an anti-addition. So stereochemistry, trans stereochemistry, one methyl's in the back, one methyl's in the front. But look at the oxygens. It's an anti-addition. The oxygen's added to the top, one oxygen's added to the bottom. This is a meso compound. Again, if we rotate around, we get an internal mirror plane. And so we only have one product formed there. But if we have the cis-2-butene, do the two-step process here, we're going to end up, again, here with the cis, methyls in the front. Here, again, they showed you methyls in the front. But here we have oxygen added to the top and bottom. In this case, this gives us RR. The opposite one gives us SS. One-to-one mixture because these are enantiomers of each other. We get a racemic mixture here. It's not always true that anytime you have a transalkene, you get a meso compound. It's not always true that anytime you have a cis alkene, you get a racemic mixture. It's not always true. You actually have to look at and think about the stereochemistry of your product. So I would say drawing the mechanism is going to be the best way for you to make sure that you are drawing the right stereochemical outcome. So let's draw the mechanism here for this. So I'm going to skip this first mechanism step because I've already shown you that. Just for the sake of time, you know that you're going to be making this oxycyclopropane. I want to show you the mechanism for the next step. So with the oxycyclopropane, we need to have these two methyls cis to one another. They're on the same side as one another. And so we can choose to either have both the methyls on a wedge or both the methyls on a dash. I'm going to put them both on a wedge, which means the other thing has to be on a dash. Now, I usually don't show the hydrogen. I'm just showing you it here so that we can all be on the same page. But usually I would draw it like this. This would be how I would draw this alkene, where you just have to know there is a hydrogen there. Now notice everything's pointed down and the oxygen is up. All right, in our next step, we have H plus and H2O, right? That's our step 2. Our step 1 was MCPBA, dichloromethane. Step 2 would be the aqueous workup step. So what happens? Well, remember when we have an oxygen, that can act as a base. So from the lone pair to the proton. This is something that we saw before. We've seen this a bunch of times before. If we had an OH and we add in some acid, what does it do? It gets protonated and we make an oxonium ion. So we're going to do the same thing here with this oxycyclopropane. Our oxycyclopropane got protonated. We use one of our lone pairs, so we just have one lone pair left. 3 bonds to oxygen, 1 lone pair. We know that has a full positive charge. We had a full positive charge with H+, so we should have a full positive charge with our product. So now we have the only thing around our nucleophile is water. And so we have water that can either attack the left side or the right side. So I'm going to number this 1, 2, 3. I'll call this 4 and 5 of that ethyl. So 1, 2, 3, 4, and 5. I'll call this other methyl 6. So 6 down here. So which carbon is going to be attacked? What did we say before? We said if the ring is neutral, we were going to attack the less hindered side. If we were attacking the oxycyclopropane, we would attack the less hindered side, but we're not. We're attacking here this oxonium ion. And so when we attack the oxonium ion, remember what we said before when we were looking at our bromonium ion? We said that a nucleophile will attack the more hindered side because we have a positive charge on that bromonium ion. Remember that? Same thing here. The nucleophile, which is water, is going to attack our more hindered side. So the attack happens at carbon 3. If the attack happens at carbon 3, we're going to be breaking the oxygen-carbon 3 bond. The oxygen-carbon 3 bond, not the oxygen-carbon 2. That doesn't make any sense. We're bringing in electrons to carbon 3. We're bringing in electrons to carbon 3. Something has to go away. We would have too many electrons there. So we break the oxygen-carbon 3 bond. So as we break that bond, what happens to carbon 1 and hydrogen? They stay where they are. But now there is an oxygen at the top. So hydrogen stays on a dash line, and we have that carbon 1 methyl on the wedge. This oxygen and this hydrogen are now over here, this oxygen and the hydrogen attached to it. We broke that bond, so we still keep this oxygen-carbon 2 bond. And that oxygen had a hydrogen on it, and so we keep that hydrogen on it. This is an SN2 reaction. What do we know about SN2? Inversion of configuration. So at carbon 3, we get inversion of configuration. This is why it's so important to draw things in the right way. Pointed down, and so you get inversion of configuration, and so these now are pointed up. Both things are pointed down in the beginning, and then on carbon 3, we move these things up. But what's on a wedge stays on a wedge, and what's on a dash line stays on a dash line. So on carbon 3, I had that methyl that I called 6, and I have my ethyl that was carbon 4 and carbon 5. But they get pushed up because I'm bringing in this bond to this oxygen of water. What is the oxygen attached to? It has 2 hydrogens. Those hydrogens can't just disappear. You have to show in your mechanism what is happening with them. And so we have a hydrogen and another hydrogen on that oxygen. 1 lone pair is left. Now this has a positive charge. This, overall positive charge. Everything that's happening here, overall positive charge. Everything that's happening here, overall positive charge. Once we introduce that positive charge with that proton, every step has to have an overall positive charge in one way or another. So what's our last step? We know that these 2 hydrogens are acidic. So you can bring in like water to deprotonate, or you can just do this from the middle of the bond to the oxygen. Why? Oxygen has a partial negative, hydrogen has a partial positive. Oxygen hates having a positive charge. And so now I can write minus H plus. So that's where the positive charge goes. So now I can be overall neutral again as the product. And so this is going to be my product where my oxygens have been added anti to one another. Anti-addition for the two oxygens. Show the stereochemistry here for carbons 4 and 5. There's my carbon 6, 3, 2, carbon 1. So this is my product, but I'm not done yet. With this product, I have my diol, my vicinal diol, and I have shown the stereochemistry throughout the reaction, so that's good. As I'm doing this reaction, I actually have this as racemic. The opposite stereochemistry is also true. This is also racemic. This product is racemic, and this product is racemic. But what I want to do is get my carbons 1 through 5 in the molecular plane. I want to redraw this product to where my atoms 1, 2, 3, 4, and 5 are in the molecular plane, and I have hydrogen and oxygen, or oxygen and methyl, coming out or in from the plane on a wedge or on a dash. So carbon 1, 2, 3, 4, and 5. So again, you have to be able to visualize this. So as it's drawn, I want to move basically my carbon 1 into the plane. So push it back just a little bit. As I nudge it back a little bit, the hydrogen ends up on the top, but in the back, and my OH ends up in the front. You should be able to visualize this. If you can't, build the model so that you can see that this is the product with carbon 2 in the plane. Carbon 1, carbon 2 in the plane. So I just nudge carbon 1 back a little bit. It ends up in the plane. Hydrogen goes to the back, but at the top. Oxygen moves to the front at the top. Now looking at carbon 4 and 5, it's in the back. I want to nudge it a little bit forward. I want to move it a little bit forward. As I nudge it forward, then I'm going to have the methyl and the oxygen at the bottom on carbon 3. If I nudge 4 or 5 forward a little bit, I end up with it like this. And so then my methyl, that's carbon 6, and my oxygen for the OH, they end up at the bottom. So which one is which? Well, if I nudge the ethyl 4 and 5 forward some, then carbon 6 moves down and pushes the oxygen to the back. So we end up with our OH in the back and our methyl carbon 6 in the front. Again, we don't have to show this hydrogen, so what I would prefer from you is just for you to draw it like this. Where you just go straight up, O, and then over to the side, hydrogen. So I had a question about overall positive charge. Well, where's the overall positive charge? This is the thing that has a positive charge, right? We have this positive charge and we have something that is neutral. But overall, we have a positive charge. Here we have our positive charge, and we're reacting it with something that is neutral water. But we get an overall positive charge for everything that's reacting there. Here we get an overall positive charge because we have a positive charge on the oxygen, and then we lose that positive charge as the proton. And so we end up with a product that is neutral. So anyway, we get this product where we could write racemic underneath it, or we can draw the other enantiomer. The other enantiomer being OH, OH. So we get these two products. So if you just drew one product and you wrote racemic underneath it, that suffices. So just writing racemic here, you don't have to draw the other one. But if you don't, then you need to draw the other one and say that they are enantiomers of one another. Questions there?
Yeah, Professor. Quick question. So, like, can we do that for everything else? Like, just draw one and say racemic?
If it is racemic, yes.
Okay.
If it's not racemic, then no, you can't. If they're going to form diastereomers, you have to draw the other diastereomer. No, you're fine. All right. So we saw that MCPBA and hydrolysis, those two steps, give us the antiproduct. But what if we want the Syn product? Well, if we want the Syn product, we have to use this new reagent called osmium tetroxide, OSO4, osmium tetroxide, THF, and then there is a second step. But we add both of our oxygens to either the top face or both of our oxygens to the bottom face. Both of the oxygens come in the same step. Here, one oxygen came in the first step, the other oxygen came in the second step, but here both of the oxygens come in from the osmium tetroxide, which allows for this to be a Syn addition. So what is the mechanism for this reaction? Well, we have these three arrows here. So arrow 1, from the middle of the double bond to one of the oxygens of osmium tetroxide. Arrow number 2, that one would have too many electrons on it. That oxygen would have too many electrons on it. So it pushes electrons to osmium, which gives us this lone pair here. We end up with this lone pair in the product. Osmium can handle having electrons on it, but the oxygen says, okay, I don't want you to be left with the positive charge, other carbon. So we end up making this bond in arrow number 1. We end up making the lone pair for arrow number 2. And then we end up making this bond in arrow number 3. So we end up with this cyclic intermediate, a cyclic ester intermediate. And so that's all that happens in the first step. And then the second step, we can use either H2S, which is hydrogen sulfide, or NaHSO3, sodium bisulfite. Either one of those can be used. So here we can use this or this. Those two things are the same. But in that second step, no mechanism here. Don't worry about the mechanism here for the second step. But just know that in the second step, we're basically breaking these bonds and we're ending up with OHs. So you can see that the oxygen carbon bond is made here in this one step. And so both of the oxygens get added. So look up here as wedges, or both of them get added as dashes. But they can't be one on the top, one on the bottom, because it's too large of a reagent. They both are going to come in on the same step with this cyclic intermediate. Think about ring strain. So it's better to make a ring where both of the bonds are on the same side than trying to have one here and then one down here. That doesn't make any sense. So we have our 3 arrows that we draw. We get this cyclic intermediate, but this is a concerted reaction. We still get a vicinal diol, but it is a Syn addition product. So again, with this product, you're going to need to rotate, and you're going to need to get all of your carbons, your longest carbon chain, into the molecular plane, and then have the OH either coming out towards you or going away from you. But you need to draw the product like this initially, and then use this to figure out stereochemistry of the product, just like I did on the previous slide. All right, so with this, sometimes osmium tetroxide is a little too expensive for the reaction you want to do. So people can use catalytic osmium tetroxide, and then you use like H2O2. So another oxidizing agent, but you use a stoichiometric amount of this. So you might see this in your solutions manual or in your homework. Questions there?
Wait, so what does the reaction look like if you use sodium, the
Same.
other, the
Same.
same? Okay.
Because this is
And-
coming in step 2, so there's no difference there. It's just you can use either one of these.
And so you said there's no mechanism for that. Is that
Correct.
because it's a concerted reaction?
No, I don't want you to worry about that because that's more, it's not organic.
All right, thank you.
I just want you to worry about organic reactions. So you do have to know the mechanism for this first step, where the osmium tetroxide is reacting, and you need to be able to draw this intermediate, but then just go from the intermediate to the product.
Quick question, Professor. So regarding any of the reactions, how much mechanism actually matter?
How much does mechanism matter?
No. How much do we actually have to show?
And if I ask you for the mechanism, you should show all of the mechanism every single step. If I don't ask you for it and you don't draw it, you might not get the right stereochemistry. So I would say draw the mechanism every time. The mechanism will help you to figure out the course of the reaction. It helps you to figure out stereochemistry. All right, this is 12-12, a new reaction here. So remember I said, in this class, we're just going to get a bunch of reactions every day, and you just got to know them. So here's our new one. It's called ozonolysis. So when we were talking about the osmium tetroxide, we were breaking only the pi bond. So going back, we were only breaking the pi bond. Arrow number 1 here, we were only breaking the pi bond of the double bond. But with this new reagent, ozone, so O3, we can break both the pi and the sigma bonds. That's rare, right? We said pi bonds are weak, sigma bonds are strong, but we can break both of the bonds here. So 1, 2, 3. We've broken that bond between carbon 2 and carbon 5 in this reaction. So for this reaction, you're not responsible for the mechanism. So again, I'm going to write no mechanism here. But for this one, you just need to know we're breaking all the double bonds to carbon, and we're instead giving each carbon that had a double bond to another carbon, we're giving it a double bond to oxygen. We're making a carbonyl type compound. So it's a two-step process. We can either use zinc and this acetic acid, or we can use a sulfur-containing compound, methylthiomethane. But in this reaction here, we always use ozone and dichloromethane in the first step. So ozone gas. So in this reaction, here's an example. You have to pay attention to where the hydrogens are. I might not always draw in the hydrogens. Actually, I won't. And so you need to know if the alkene is drawn like this, you need to remember that there is a hydrogen there, which will give you an aldehyde product. So remember, this is a ketone, and this is an aldehyde. Aldehydes have the hydrogens. Aldehyde has the hydrogens. But anyway, 1, 2, 3, 4. When we break that bond between 3 and, here we'll call this 5, we'll call this 6. We end up with 1, 2, 3, 4. Carbon 3 now has a double bond to oxygen. Carbon 5 has a double bond to oxygen. It still has 6 and it still has the hydrogen. So now it is an aldehyde. When we have an aldehyde, we do show the hydrogen. This needs to be shown. When we have an alkene, though, I won't necessarily show that hydrogen. But when you turn that alkene, so carbon 5, you turn that into an aldehyde, make sure you show the hydrogen that's on that carbonyl. Remember, this is called a carbonyl group. So I'm redrawing it, right? I want to draw it in the cutest way possible. So here, my carbon 4, 3, 2, 1. I want to have my zigzag pattern. Same with this, 5, 6. I want to have my longest carbon chain on the horizontal. And then I want to have my double bond to oxygen either straight up or straight down. Double bond to oxygen either straight up or straight down. I always want to show my carbonyl that way. So that's it. That's our ozonolysis reaction. Questions on that? This should be one of the more fun ones, I think. Everything's fun. I know some of you guys love the E2 reaction. I heard yesterday someone was an E2 kind of a guy. So I know you guys have your favorites, but this might become one of your favorites. All right, we're skipping 12-13, starting with 12-14 now, polymerization. Polymerization. So this is how we make a polymer. We start off with an alkene monomers, and we use the alkene monomers to make a polymer. So I'm going to number this. I'll call this, well, I'll do AB. So if I call this A and B, this is the exact same alkene over and over and over again. A bunch of this same alkene. It reacts with itself. An alkene reacts with itself, so a bunch of the same exact alkene. That's why I'm labeling it AB, 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 AB. So here, this would be B, where it reacted to make a bond to A of the next alkene. And then B reacted to make a bond to A of the next alkene. And then again, B reacted to make this bond to A of the next alkene. So notice the arrow. We're drawing from the middle of one alkene bond to the next carbon, middle of the bond to the next carbon, middle of the bond to the next carbon, because we're making this single bond. And so we go from an alkene to this long chain alkane. Long chain alkane for our polymer. So to do this reaction, we have to have something around. If we just have alkene sitting, it's not going to react with itself. We have to have some kind of a catalyst to make the alkene begin to react with itself. So we have to have acid, base, radical, some kind of a transition metal. This will cause it to react with itself. If 2 of them react, we'll get a dimer. If 3 alkenes react with themselves, trimer. Beyond that, we call them oligomers. And then once it's like thousands, we call it polymers. So thousands and thousands of these alkenes reacting, we call it a polymer. So this is just the basic of our polymerization reaction. Let's look at some polymers. You know a lot of these. So polyethylene. Polyethylene, this is used for food storage bags, containers also. So think about Ziploc bags, polyethylene. PVC piping. Some fabrics are made out of PVC. You've heard of vinyl flooring. Vinyl flooring has this kind of this kind of PVC in it, or other kinds of vinyl groups. But we have PVC pipes and vinyl fabrics. This would be the repeating polymer. So we have this group repeating over and over and over again. Notice that we have this open bond and this open bond, meaning it's extending. This repeating thing is extending to the left, it's extending to the right in both directions. This same monomer unit repeated over and over and over again. Teflon, you guys have Teflon covering your cookware. This is the molecule. It's this carbon with 2 fluorines, another carbon with 2 fluorines with a double bond to each other, becoming this alkane, long chain alkane. Polystyrene, styrofoam containers. Styrofoam containers, it's this polymer with a benzene ring attached. Orlon is something that is present in some clothing. Plexiglass, this is the repeating unit that we see. It has this ester and it has a methyl attached to the same carbon, but this repeating in either direction. And then elastol is a compound that was made for cleaning up oil spills, because you know oil and water don't mix, and so we can use this polymer to clean up oil spills. But looking at this, as I said before, we get these long chain alkanes. So long chain alkanes are very stable, right? They don't react. So it's cool, but at the same time, when we make these polymers, you see all these different things, these polymers that we make, we don't really have ways to break them down. And so they end up polluting because we get these long alkanes. Alkanes are pretty much impervious to all other reactions, so we can't break them down into other things. So once you make a polymer, you kind of have a polymer, and it's just kind of hanging out until Jesus comes back for us And he deals with those polymers himself. But we don't have a way of dealing with them right now. People are coming up with plastics now that can break down, that are biodegradable, but that's still an area of research. All right, so let's look at one of these reactions. So this is an acid catalyzed. So we have catalytic acid here. This is an acid catalyzed dimerization. So what is the mechanism? We have here, so I'll call this 1, 2, 3, and I'm going to number the other molecule differently. I'm going to call this 4, 5, and 6. But no, they're the exact same molecule. I'm just numbering it differently so we can keep track of the two molecules. So what happens initially is we protonate the double bond. And so when we protonate, this is our Markovnikov protonation. H goes where there are more H's. And so we end up with a tertiary carbocation. So with this is 1 here, this is 2, this is 3. Now we have another alkene. So we have a carbon that's electron deficient, carbon 2, and then we have an alkene between 4 and 5. So we can use the electrons in the alkene to attack carbon 2. And so we make a new bond. So look at this, 1, 2, 3. We're making this bond between carbon 2 and carbon 4. Why between carbon 2 and carbon 4 and not carbon 5 and carbon 2? Well, this is still Markovnikov. What did we say? H goes where there are more H's, or the electrophile goes where there are more H's. So what's the electrophile? Carbon 2 is our electrophile. And so our electrophile goes where there are more H's, and so it gets bonded to carbon 4 because that has more hydrogens, so that carbon 5 can be a carbocation. And then we have our carbon 6. So at this step, remember we said this is catalytic. And so we can regenerate the catalyst by deprotonating. So we lose the acid, we added it in, then we lose it in the end. We deprotonate, so we can either break this bond that they're, this arrow that they're giving us that they labeled B, or this one they labeled A. If they did B, we'd end up with this double bond. So 1, 2, 3. Here, this is 4, 5, and then one of these methyls would be 6. If we did A, then 1, 2, 3. Here's 4. Now the double bond is between 5 and 6. So this would be a dimerization. We're making a dimer. We took these two alkene building blocks, had them react together, and we're making a dimer. But both of these products are dimers. This is the way to stop the reaction. We can stop it here by removing acid. But what if we don't want to stop it here? What if we want to keep going? Well, if we add in, so again, we add in more acid, then we can have the two dimers react with each other. They can react with each other. So here we have, we can protonate, and we end up with here, this carbocation. So 1, 2, 3, 4, 5, 6. We'll call this 6, so 7, 8, and 9. So here, we're not having the two alkenes react with each other. We're having them react with another one, but they can react with each other. We'll talk about that in a minute. But we're having them react with another one of the same exact monomer units. But what happens? Again, Markovnikov addition. And so as we do this, 1, 2, 3, 4, 5, 6. Now this is 7, 8, and 9. We can bring in another one. We'll call this 10, 11, and 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. We can keep doing that exact same reaction, bringing in another one of these and reacting with the carbocation, and then making another carbocation, bringing another alkene, reacting that, bringing another alkene, and we are elongating the chain. So here we've added 4 of these monomer units. So here at this point, we just call this an oligomer. We just call this an oligomer. And so we are elongating this chain. We initiated it, but we're always going to have this positive charge that can react with another one of these alkene monomers, elongating it over and over and over again. to get this really long chain that will go from being an oligomer to having thousands of these units, these repeating units, where we get now a polymer. So when we start this, as I said, we can proceed to make a polymer that has many of these units, but what do we need to do? We keep the temperature low to minimize E1. Remember, eliminations are favored at higher temperatures. When we have carbocations, they can do eliminations, giving us the alkene. So if we want to get the chain length to be long, we don't want to stop it, we keep the temperature low. If we increase temperature, that's when we'll stop the reaction, because we'll start to do the elimination. But we can use any kind of acid catalyst. Here's some examples: H2SO4, HF, and then a Lewis acid, boron trifluoride. But that will allow us to elongate this. So N-1, we're elongating this chain. Keep going, keep going, keep going. We have a bunch of these repeating units here. And then in the end, we stop the reaction and we end up with an alkene, one of those alkenes that we talked about initially. Note that this is a mistake in the book. They didn't have that 2 there. So if you're looking at the book, it should have a 2. But that's our first reaction, the acid-catalyzed polymerization. We use acid, start the reaction, and we keep going. So here's 12.14. We can do that same type of reaction, but now it's a radical reaction. So what did we say? When we use this kind of an arrow, it's for an ionic reaction. When we use this kind of an arrow, it's for a radical reaction. So for a radical reaction, go back to chapter 3 when we were talking about those. Think about everything we said with those, but we need an arrow to show where each of the electrons is going in the double bond. So here we have some kind of a peroxide. So an organic peroxide, R being some kind of an alkyl group. We have this peroxide, we can break the oxygen-oxygen bond, giving us 2 of these oxygen radicals. So from the middle of the bond to one to the oxygen, middle of the bond to the oxygen. These radicals are very reactive. And so then we can react them with an alkene. So this is our initiation. We react them with the alkene from the unpaired electron into the middle. From the middle of the double bond into the middle, we're making an oxygen-carbon bond. From the middle of the double bond over to the carbon, we're making this carbon radical. We're making this carbon radical. And so we know that with that, now we can propagate our reaction. So even though this is shown here over to the side, it's really here. So really your arrow needs to be like this. So just keep that in mind. This is just how the book showed it, but just know that this is how we should show it. But once we initiate it with this oxygen, then we can keep going. We have an unpaired electron, that's going to react with another alkene. And so we end up with this alkene where we put an unpaired electron on that carbon. So with that, now we can react with more of the alkene, again doing the same reaction. We elongate the chain, keep elongating it, where every time we stop, we end up with this long chain with an unpaired electron on the carbon atom. That can keep reacting in our propagation step. How do we stop it? How do we terminate? You know the termination steps. You already know those from chapter 3. So think about the different termination steps that can occur that will allow for us to stop this reaction and end up with something that is not reactive. Remember, radicals are very reactive. We need them to react with each other. If 2 radicals react with each other, we stop our chain reaction. So this is our radical polymerization. This happens to make the polymer polyethylene. It's a radical reaction. We don't make it in a linear structure. There is branching, so it doesn't just go, oh, nicely, CH2, 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 all the way in a line. What happens is that we end up with this CH2 where one of the hydrogens gets abstracted. So we are continuing this either direction, but somewhere in the middle, we end up with this carbon that is a radical. And so when we end up with this carbon that's a radical, we can react middle of the bond into the middle, from the unpaired electron into the middle, from there, we end up making this bond here, where now we are continuing that CH2 chain down. we've added in a branch. So we can make these new radical centers. So new radical center, that's what I'm showing here, a new radical center in the middle of this long chain, and then we can continue adding to that chain in that way. So we have HDPE and we have LDPE, low density and high density polyethylene. High density polyethylene, lots of branches. Low density, not a lot of branches. But those are two different kinds of polyethylene. If you look at your bottles, it actually has this letter on some of your bottles, and you can see what kind of a polymer is used there. Anyway, that's all we'll do today. So we're going to finish up our polymers, finish up this chapter, go into the learning checks. Make sure you do the learning checks before Monday so that you can be ready for what we're going to do. So you can just check your work rather than trying to copy down everything that I write. All right, if you have questions, you can stick around, but I love you guys. Have a great weekend. Be safe, and I will see you guys on Monday. Bye.
Thank you.
Thank you.
Bye.
You're welcome.